Okay, welcome back. Now, a little announcement before our next talk. At the very beginning, we're going to need your smartphones, so could you just take them out and have them ready at hand, because we are going to need them, all of them, in just a moment. I'd like to introduce our next speaker, Phil Nash, and Phil is the original author of the C++ test framework Cat2. He's also a member of the ISO C++ Standards Committee, organizer of C++ London, as well as co-host and producer of CPP Cast. He's previously worked in finance, mobile and development tools, but recently became fully independent, offering training courses in, of course, C++. More generally, he's an advocate for good testing practices, complexity reduction, and correctness. Now, Phil also has an artistic side and has been known to put his talent to the art of songwriting. And he even created a piece on C++ built systems. So let's have a quick listen and a quick look. And feel free to take your phone and switch on the torch. Thank you. And wave along. And here's the piece.
When I was young, I'd never need to use Conan. Make config was just for fun. Those days are gone. I build myself. Don't want your lips. I build myself from the source.
The best developer among singers and the best singer among developers, Phil Nash.
I never need to use.
Is that going to stop? Well, thank you for that. That wasn't my idea. Welcome to Modern C++ Error Handling, where I won't be doing any more singing, you'll be pleased to know. So I am Phil Nash, as you heard in the introduction. In fact, it's covered most of the things that I would normally have said. But I will just quickly do the logos. Although I will first of all say, I'm a regular conference speaker. I think I recently counted, I've done about 200 conference and meetup talks, which is far too many. You shouldn't learn by my example. But this is my first time at Code Dive, so thank you for having me here. Can tick that one off now. So the logos, as you heard, co-host of CPP Cast. Who listens to CPP Cast? It's a bit hard to see in this lighting, but I think that's everybody, just for the record. Just in case not, if you listen to podcasts, you should definitely check out CPP Cast. We've got one of the original co-hosts in the front row here as well, who'll be doing a keynote later. That's Jason Turner, of course. Shaved Yaks is my own company. I went independent earlier this year, as my intro said. So I now do training, run some other conferences as well, and I'm writing software. But just recently, I've also started doing some work with Undo as a developer advocate. They do time travel debuggers. I'm not going to talk about that now, but if you do want to hear more about time travel debugging or thread fuzzing, do catch me afterwards, and we can talk more about that. But we're going to talk about error handling today. And I've put the modern C++ prefix on there. And it's a very deliberate choice. It's not just for the meme. Because I've actually done a couple of talks on error handling before, both pre-pandemic, both pre-C++ 20, which is significant because both of these talks were quite forward-looking, especially the second one, looking at things that weren't in the standard yet, that were going through the pipeline, and some that were even a bit further off. Which was really interesting at the time, but now they're a bit dated because some of those things haven't really panned out. Some have actually made it into the standard, and they look slightly different to what I talked about then. So I thought it was time to do something updated. What we can actually use today, what we should use today, how that works, and mix in a little bit of new stuff as well. So that's really what this talk is about, bringing us right up to date. So let's get started. Now this talk is divided into two parts. This first part is going to be the longest part. A series of total disappointments. There's a couple of little minor jokes in there, but the disappointments word, it's not something I've made up, something that's been around for a few years. And it's this idea of an error path that is predictable. You know that it can happen, you're just a bit disappointed when it does. But you do need to write code to handle it and maybe do something else. So all sorts of things fall into this category, and we're going to cover many of them in this section, including exceptions, but also error codes, and as we'll see, optional and expected. So, because this material has a lot of code in it, it can get a little bit dry. I asked ChatGPT to generate me a whole series of robots that are going to help guide us through this. So look out for those. Here's our first one. And we're going to work on this example. Very simple function, parseInt, takes a string view, returns an integer. You can sort of guess what it's meant to do. And I put in a very simple, simplified implementation. Don't get too distracted by that. It's just slideware. But it does show us that there is a couple of paths out of this. And you can see there's a couple of return statements in there. There's not really any error handling in this, at least not yet. That's what we're going to add. So you can probably see there in the middle, the first non-numeric digit it finds is just going to return out with whatever it's got so far. Let's see what that looks like in practice. So I've got a few different values we're going to pass in. We're going to see this a lot. So we're going to pass in the string 42, of course, and that's going to parse correctly to 42. If we say 42x, because it stops at that first non-numeric digit, it's just going to return us the 42 it got so far. If we start with the x, then it just returns 0, because it didn't accumulate anything, but it started with a 0. Now, that sounds pretty useless. Bear in mind, this is actually the behavior that IO streams gives you by default. You stream a string in and then try to stream an integer out. You'll get a 0 if it didn't actually manage to parse anything. Can actually be useful sometimes. That might be what you want. But you can't distinguish that 0 from an actual 0 that was in the string. Usually you're going to want to do that. So what can we do? Well, one thing we can do is actually to write a separate function whose only role is just to validate that string. Now, you might think that's a bit silly. No, we should do it all in the same function. We'll get to that, but there are cases where this is actually appropriate. Because you don't always actually want to parse a string. You just want to tell whether it is an integer. So it can be worth having this anyway. But we will address the redundancy in a bit. So all this is doing is just finding if there's any non-numeric digits and returning false if not. So here we have some error handling. Well, really, it's the purpose of the function, but we're just using a boolean. That's completely appropriate still. If you just want a yes, no answer, is this thing or not, boolean is perfect, of course. This is modern C++ error handling, so I'd be remiss if I didn't bring no discard into it. Not as useful here as it is in some other cases, but do get into a good habit of using no discard on functions where the return value is actually really important. So we'll put no discard in there. I'm not always going to use no discard or const or no except or any of the other things that might belong on some of these functions. It is slideware, but I will try to remember to put them in where it's appropriate. All right, so in usage, we can write some code that just calls it int, takes a different path. Nothing too surprising here yet, but just to show you, that's what we're going to get out of that. OK. Now, the problem with this is those two error cases, the one where we have some initial numeric digits, and we do actually parse a string out, potentially, and the one where we start with no leading numeric digits. We can't distinguish between the two with the boolean. So we could change that to an enum, of course. This one just three states, it's fully numeric, starts numerically, or it's fully non-numeric. That's really the only difference we're making. Again, pretty straightforward. But now we've distinguished between those two cases. Great. Okay. All right, let's get to that redundancy, because we're doing all the same work again that we're going to do in parseInt. So calling this and then parseInt, doubling the work, doubling the implementation. We don't want to do that here. So what can we do? The trouble is, of course, with this parse status or the boolean, that's sort of blocking the return channel. We're already returning something, so we can't return the actual value anymore. We have techniques to work around this, even some really old ones. Out parameters. I'm sure you've all used out parameters in the past, usually taken by reference. So one of those return values, instead of returning, we'll pass it in, we can set it in the body of the function and return. This works. It does the job. We've done this for a long time. I'm sure still sometimes can be a case for it today, but probably not too much anymore. But it does the job. Actually, the biggest problem with this, for me, I think, is that it prevents sort of functional composition. We can't really take that return value and then pass it into another function. We have to store it into intermediate values. Just a very, very brief mention, another older technique, setting a global variable like erno. But this is not really how you use erno anyway. It's got all sorts of problems. Don't do that. We won't discuss it in too much depth. The first real solution, not particularly in modern C++ these days. Exceptions have been around for a long time. Fallen out of fashion a bit in recent years, and I've talked about that before. But still, the default choice for error handling in C++, and a very good choice. Solves all the problems we had. Doesn't interfere with the return channel. Doesn't change the signature at all, in fact. And it shuffles all the error handling off to the end. Very low, maybe zero overhead on the happy path. Really good choice. So I want to be clear, because we're going to talk about lots of other different options. Exceptions are still a really good choice if you can actually use them on your project. A lot of projects can't. Some justifiably so, many not. But if you can use exceptions, they are still a really good choice. And just to address some of the criticism against exceptions, do watch Khalil Estell's CPPCon talk, C++ exceptions for smaller firmware, which sounds like a contradiction, but, well, watch the talk. I won't give it away, but he basically says that most of this overhead we can get rid of. So if you thought exceptions were too expensive, watch this talk first. That's all I'm going to say about exceptions for now. They'll come back briefly a bit later. But modern C++ error handling. We get to C++ 17, we got stood optional. We've had that for a while now. I'm sure most people are familiar with it. I won't spend too long on this, but let's just see what that example looks like if we use stood optional. So now our return value is stood optional of int. And in the error return case, we just return an empty optional. Otherwise, we return the actual value. And in usage, behave a bit like a pointer. We can test it in an if statement. We can dereference it if we've got the value to get the value out. And otherwise, we know we didn't get the value for some reason. So pretty nice, actually. Nice, clean way to address this. And actually, one of the problems with exceptions, the actual problems, is it's not very good for control flow style error handling. And sometimes that's what you need. A function like this, where we just maybe want to test whether a string contains an integer, we don't really want to use exceptions for that. So this is actually quite a good approach. But we've taken one step back at the same time. We've lost that ability to distinguish between the different error cases. So good start, but can we get back that additional ability? All right, move on to C++ 23. Now the current standard, as of quite recently, ironically. We have stood expected. Much newer. You may have heard of it. You may have even used it. But it's still going to be a little bit less familiar to most people. So we'll spend a little bit longer on this. So stood expected actually looks very similar to stood optional. The only real difference is we've got a second template argument, which is an error type. Now, I've used an exception type here, stood runtime error. Don't be distracted by that. You wouldn't normally do that. And I actually regret putting that in the slides, and I thought about changing it later, but it's actually for a load of slides, so we're stuck with it for now. But it does show that you can do that. So In the error case now, we can return 2 different exceptions depending on whether it's the first digit or not. And then we can test that in our usage. So in our test usage code, the happy path is exactly the same as optional. We can test in the if statement, we can dereference using the star operator. But in the error path, we've now got this dot error. It gives us the error object. In this case, it's an exception, so we can do dot what on that to get the message out. Again, I probably would have written this with that enum that we saw earlier instead of an exception type. Don't be too distracted. But that solves the problem. It's actually pretty good. Nice, clean, easy to use way to handle error cases or unexpected cases more generally using stood expected. The problem is, and it breaks down a bit, and this is true with stood optional as well, when you start to scale up, when you have multiple bits of code that all have different types of error handling using stood optional or stood expected. This one, we've only got 2. And you can see it's actually a lot more complicated. I'm going to just walk you through this. Don't worry too much if you don't follow it all. It's not that complicated, but it's just lots of little bits. So let's zoom in a bit. So we actually start on line 3, which is part of the problem. We're calling parseInt, same parseInt as before, returns a stood expected of int and stood runtime error. We put that in an if statement. So in the happy path block, we know that we've got an integer, so we can dereference our expected, subtract 1 from it, and we've got a new integer. Well, so far, so good. But then the next thing we want to do, and yeah, I admit this is a little bit contrived, we want to divide it into 1, so sort of take the reciprocal, which means we've got to guard against division by 0. So that's why I put that in there. So we're going to test first. Is this integer 0? If not, then we're happy path. We can carry on. But otherwise, we've got to create another stood expected. And notice now, because we're actually dividing into a floating point number, this one's going to be a stood expected of float and stood runtime error. So we can't use the original one anymore. And that's why we had to pre-declare it at the top. So we're using assignment in both of these cases. But then if the outer if block, we went into the else clause right in the middle there, we had an error. Well, now we got this, we actually need a stood expected of float, and we've got a stood expected of int. So we need to move the error out of there into our new stood expected of float. Finally, we've got our stood expected of float, and we can test it and dereference it at the end as before. So yeah, it's not rocket science. You can follow it all, but it's a lot of tedious little details you've got to get right. And look, the happy path ends up in the middle. We started a few lines in. I mean, maybe we can put the happy path at the end a bit if we just invert the if conditions. Exactly the same code otherwise. We just put the happy path at the end. But it's not really that much better. So what else can we do? Well, a big problem here is this anti-pattern that you see a lot of, well, we need to set something based on some conditions. So we're going to have to pre-declare an uninitialized or default initialized value and then assign it later. Whereas really, we wanted to do that all in one go. And there's just a general pattern to solve this, to rewrite that, which is to use an immediately invoked lambda expression. Fairly well known now. Probably most of you are familiar with this, but just in case not, you see we've introduced a lambda right at the start there, which is returning our final stood expected of float. It's capturing the string on the way in. We're doing all of our conditional stuff inside of there, but instead of assigning inside, we're returning out of it. And that return can now be used to initialize directly our stood expected of float. You can see it's being immediately invoked at the end there. So it's just a nice way of addressing that nice general pattern. If you haven't really used that before, I encourage you to do so. That's not what this talk is about. But there is one way that we can clean this up a little bit. It's OK. It's not too bad. But we can do better. We're using stood expected here. We've already got C++23. C++23 introduces some additional functionality, the so-called monadic operations. for both stood expected and stood optional. So there's the 4 member functions I'm going to introduce you to. 3 of them are shared between both types. The 4th one is stood expected only. Let's see what we can do with those. Now, we've got Monadic up there. I'm not going to talk about monads. You don't need to know what a monad is to understand this, just what the functions do. So let's go through that. All right. So we start with parseInt. So it's much better already. Now, parseInt is returning our stood expected of int and stood runtime error. Now, stood expected has these methods on. So transform is the first one we're going to use. They all take lambdas. And those lambdas take what we call unwrapped values, so that the dereferenced value in this case. So we've got an int coming in. We don't need to check it first. Transform's only going to get called if it has a value, and it will call it with that value. So that's a bit simple already. And in there, we just do that return I-1. Nice, clean, simple. That is going to then rewrap that back up into a stood expected of int and runtime error. And now we can call the next member function on that. And we're going to use .andThen. And .andThen also only gets called if you have a value, unwraps the value, passes you that. You don't need to worry about that. But this time, it actually returns a new stood expected. So that's why we've had to spell it out there. And we can use our stood expected of float. And now we've got our check against 0. We've got our divide by 0 error case. Again, we can just use returns here. So that's also a bit cleaner. Now, why do we have this difference between transform and then? Let's say with and then, we can actually spell out the whole stood expected return value. And in this case, we have changed the value type. That's not the reason we had to do it here. We could have done that with transform. That can also change the value type. But we also needed to be able to return either a value or an error again. So this one is doing error handling. So and then does error handling. Transform will only transform the value to another value. That's the difference. And then finally, we've got our final expected of float. We can do our usual test at the bottom. So far, so good. So but let's compare that with what we had before. That's sort of the best we had without these functions compared to this. So not a lot less code, but it is a lot simpler. Once you get used to these functions, it's a lot simpler, a lot cleaner. And look at the control flow, or the data flow. We start with parseInt. The integer goes in at the top, goes through each line in succession. There's none of this in and out, heavy nesting. Much cleaner once you get used to it. All right, I said there were 4 Monadic operations. This is 2 of them. Another one is or else. We could tack that on at the bottom. So or else will get called in the case of an error, and it will actually pass you the unwrapped error. We're not using it in this case, that's why I just put auto there, but you can get the error if you need to operate on it. And then it returns a whole stood expected. Again, you can change the types if you want. But the idea here is that you can provide some sort of default or backup value. It's a bit like value or on stood optional. In fact, expected has value or as well. But value or is eager in that you have to give it a value that you've pre-computed if that's an expensive operation. Whereas or else is lazy. You're giving it a lambda. That lambda is only executed if there is an error. So you can actually have some sort of computation in there. You also have access to the error object. So you may need to take that into account. And you can even provide a return an error from here as well. So it is more general, more flexible. But you can use value or as well. And that means at the end of this, now we're guaranteed to have a value in our expected float so we can safely dereference it. All right, that's or else. There was one more, which is transform error. Now this is the one that's unique to stood expected, and perhaps for obvious reasons, because it actually operates on the error value, which optional doesn't have. So if it is an error, like with or else, you get called with that error. This time we are using it. But like transform, rather than returning the whole stood expected, you only have to return a new error value. It's just literally transforming that error object. It can be a different error type, as we're doing here, but we don't get to change the value. So here we're just taking the message out of our exception type, wrapping that in a string, and returning that. So at the end, when we say .error, we just get a string back. Fair enough. Bit of a contrived example, but hopefully illustrates how this all works. So just to summarize the monadic operations, these are the 4, and then or else transform and transform error. The first 3 shared between stood expected and stood optional. The last one specific to stood expected. A couple of other minor differences as well. Or else for stood expected gives you the error object. There isn't one for optional, so it doesn't give you that. But otherwise, they work the same way. This might be a little bit easier to sort of internalize, because I think that's the big difficulty of this, is actually internalizing all the different semantics. If you put it in this grid, it really sort of divides up across 2 dimensions. So, and then and transform deal with values, or else and transform error deal with errors. And you get the unwrapped versions of each. And the other dimension, and then and or else, will always return a stood expected. You've got to construct a whole new stood expected, which means you can do error handling if you want. Whereas transform and transform error, you stay in the world of values or you stay in the world of errors, which is much simpler if that's what you want to do. So you have the choices. You could actually just stick with and then or else and do everything that the transform functions do. But if you can stay in the world of values or stay in the world of errors, then it's cleaner to do that. And really, that's all there is to it. It's just a case of familiarity. Hopefully, that example has shown that it does clean things up a lot. It's worth learning. It gives you a lot. So that is the error handling features in C++ 23. Stood optional, well, we already had. Stood expected, we got. And these 4 functions. But that's not the end of this talk. We have another section to get through. So, part 2. Now, while the whole previous section was mostly language dependent, C++ 17, C++ 23, we got into a lot. This section is going to be mostly language version agnostic. You can use what I'm going to talk about in any language version. We will talk a bit about contracts, particularly towards the end, which are an upcoming, hopefully, language feature. They are still on track for C++ 26. Not a done deal yet, so we'll see. But although I'm going to mention them, we can do everything that we're going to talk about without them, so don't worry too much about that. We can also mix in things like stood expected as well, as we'll see. Now, for this, we're going to use a different example. So it's almost like the inverse of what we had before. We had a parseInt, took a string and returned an integer. Now we're going to take an integer and return a string. Okay, but it's not quite the reverse. As you can see from the name, we've got some expectation on that integer. So month as string suggests that this is going to be a month number, and we're going to return the name of the month. So again, let's look at a possible implementation of this. Simple enough. We've got an array of month names at the top, some sort of global or static. And we're just going to index into that. Nice and simple. Does the job. We've got a -1 on there, so our month is 1-based, 1 for January, and so on. Which means 0 is out of bounds. And that's the thing. This function is only valid for integers between 1 and 12 inclusive. Anything else is going to be undefined behavior. And that's something we need to be very careful about. Now, we can get rid of the undefined behavior. Oh, before we get into that, let's just actually see what the undefined behavior looks like, possibly. I ran it on my machine with these 3 values, and this is what I got. So the first case where I passed a 0, I actually got an empty string. In fact, I think most of the numbers past 12 initially just gave me empty strings. And that's the thing with undefined behavior. Sometimes it seems to give you something reasonable, but it's lying to you. It took about 10,000 before I actually got into some garbage memory. But that's the thing with undefined behavior. It can be misleading. Sometimes it seems like you're getting away with it. We don't want to invoke undefined behavior, but it can be useful to have it in the code. And it's a big hot topic at the moment, but right now we still embrace undefined behavior in the code. We just want to put in ways to avoid actually invoking it. So I said we can actually remove it completely by turning this into an error handling case. So this is like the disappointment handling, whole of the first section. We just talked about any of those techniques, including exceptions, stood expected. We can do a test up front. In this case, we're throwing an exception, and we never actually get to the undefined behavior. So that's a perfectly valid approach to doing this. But if you do want to keep the undefined behavior, because that avoids doing that if statement, and that may matter to you, there's other reasons as well, then what can we do? Well, we could do the check externally. So here you can see it's off in the test if function. So we've taken the check out of Mumford's string. We're always going to make sure we pass it valid data, so we'll do a check there. But it seems like all we've done is just push it up a level. But this does give us an advantage, because now we can do that check just once, and we may call Mumford's string many times, or several functions like it, that all depend on Mumford's string being validated. We've validated our data, and now we can call functions that depend on that. Okay, so far so good. Now, just because we are not choosing to do this as error handling, doesn't mean that we shouldn't check that range at all. So we should probably put at least an assert in there, so that in a debug build, it's still going to be doing that checking and will let us know if we've got a bug in our code that's invoked that undefined behavior. We want to weed that out. So if we do get contracts, as we're going to see a little bit later, there's other ways to achieve the same thing. In this case, an assert is perfectly fine, so I would at least do that. But now we've got some duplication. You can see our range check is in the code twice. That's also dangerous, because that can get out of sync. And now if it gets out of sync, we're going to be exposed to that undefined behavior again. If only we had something in C++ that lets us deduplicate bits of code. Of course we do. We can refactor that out into a separate function. I'll call this one isValidMonth. Now we can use that in both places. Technically, there is still a little bit of duplication here. I've got that function name, but an identifier repeated is much better than some detailed logic with consequences. So this is a much better situation. But it's still a bit painful to have to do this if check every time and remember to do it. Is there a better way? Well, if you're doing something a lot, again, what do? You factor that out into its own function or class, whatever the abstraction is. We could do that as well. So we can write another function. I'm going to call this one Mumford string checked. And in there, we do the if check. In this case, we're going to return the stood unexpected instead. So we can use any of these error handling techniques. And if it passes the check, then it's just going to forward on to the original function and return that instead. And now we can use Mumford string checked anytime we need the safer version. So we could do this with exceptions as well. But we've got the choice. We can opt in, we can opt out. But we've got a bit of extra boilerplate now. 2 functions instead of 1. A little bit painful. We'll address that in a minute. Before we do that, one more thing. We've chosen to have a longer name for the safe version, the checked version, which sort of implies that the default is the unsafe version. Nothing to stop us just switching that around. So now we have Mumford string unchecked, which you can opt into. Well, the default is now the safe version, which actually checks. And you're more likely to use that, because that's just how we are. So starting to get there. We've got the choice. We can use the contract version, we can use the checked version. But I mentioned that boilerplate. Well, let's just change our error handling to exceptions, because now we've got the same signature for month for string and month for string checked, apart from the name itself. Which means we could actually do something interesting. So bear with me on this. If we make it a template, we've got an enum here for checked and unchecked, non-type template parameter. Got the enum, defaults to checked. You can do it the other way around if you prefer. And inside the function, we're going to do an if const expr. So if we're in the checked mode, we'll do our check, throw an exception. Otherwise, we carry on with the unchecked version. We've still got the assert in there, just in case we skip that. You notice in the usage code, we don't even have to put the angle brackets in if we're using the default. So it just looks like a normal function. But if we want to opt into the unchecked version, we'll just apply that template argument. So one function gives us both approaches to dealing with that error. Not too bad. We've still got a bit of duplication in there. Now, I said it's minor duplication before, the two calls to isValidMonth. Now they're right up against each other. It just feels a bit like, can we do something about that? Best I've come up with so far, maybe there's a better way, let me know. If you could tolerate a macro, we can hide all that boilerplate in there. But it's not bad. Assert or throw just looks like an assert. Now I've put spelt out the whole exception call there. If you can go with default version, we can make this just like an assert. Not too bad, considering what that's giving us. So, not too bad. I think we can still do better. Might actually be more code, but I think it's going to be better in the long run. Because the problem here was the difference between the range of the int, which is, 4 billion, with what we call the domain of the function, which is expecting a number between 1 and 12. It's a big difference. And all of this has been in service of just bridging that gap. And where possible, I prefer correct by construction techniques. Probably familiar with this term. Let's see how it applies in this case. Really, in this case, it amounts to having some sort of strong type around our month abstraction, because that's really what we have, this implicit abstraction of a month that we're having to sort of check around the code. Let's just centralize that in a single abstraction. We'll call it month. Now, you can use third-party bounded integer libraries that would cover you in this sort of case. But this is a more general approach anyway. It's actually not that much code. Although, I mean, this is slideware, but you don't need a lot more than this. We're just going to wrap that integer in there, but we're going to validate it on construction. Literally correct by construction. So if it's not valid, in this case, we're going to throw an exception. We can still get the value out using the value method. Now in usage, month for string, instead of taking an integer, takes our month type, already pre-checked. Again, as I said earlier, if you've got many calls to month for string or other functions that all take months, you don't have to keep checking. You don't have to worry about was this checked or not already on this code path. If you've got a month, you can guarantee it's already been checked. Correct by construction, really simple approach to just centralizing any actual checking. Now, because we've done that, we can push that checking as close to any boundaries as possible where we might get unvalidated data from. But there can still be some cases where you say, I know I've got an integer that's guaranteed between 1 and 12. I want to construct this month without any overhead. So we sort of need another constructor, but we can't give it a different name. So I'm going to use what we call tagged invocation. So just write an empty struct at the top with unchecked. That's our tag type. Only purpose is to provide us an overload. So now we've got another constructor which takes unchecked as its second argument. Doesn't use that, it's just for the overload. And in usage, we just pass a default constructed unchecked in. And usually, this can get optimized out Last time I said that, I got called up. Somebody said, but I put this in Compiler Explorer and there's still some overhead. Maybe sometimes do measure if that's important, but usually you should be able to get away with it. So worth bearing that in mind. Now we're back to all of the opt-in, opt-out that we had before. We pushed the check-in closer to a boundary. We've got nice, easy to reason about types we can use anywhere, and they're always checked. Okay, running a bit short on time. I still want to talk a little bit about contracts. Now, I said we're not going to rely on having contracts. They're not quite here yet. This is not a talk about contracts. I recommend a talk by Tima Dumler, one of the authors of many of the contracts proposals, who did an excellent talk at CPBCon on that. Not sure if that one's available yet, but do watch out when it comes out. There was also one by Lisa Lippincott, which is a bit more the philosophical angle to contracts. So watch one or other or both of those talks. But if we did have contracts and we wanted to solve the same problem, let's go back to just the free function version, keep it simple. Then we would put this precondition check, actually between the name of the function or the function signature and the body. So you can see it's outside the curly brackets. But otherwise, it looks very much like the assert we had before. And it's playing basically the same role. Main advantages are finer grain control. We'll see a little bit more of it in a minute. It's sort of part of the interface, so you can often see it outside of the function for different purposes. And it's just a bit more expressive as well. Now, we don't have this yet, but, the other advantage, by the way, is we actually get a lot more information out if something fails. We can get something pretty close today if we're willing to write another macro. So, slideware. I only put this together for the purpose of this slide. This is not a proposed library or anything. And it doesn't exactly match the contract's proposal. It's just enough to demonstrate the essential points here. So very much like the assert macro, but one thing to notice is this violation handler. So if a precondition check or any contract check fails, rather than just immediately aborting, it's going to call this violation handler with the stringized version of the expression that failed. So here's my implementation of how to deal with that. I'm not going to go through this in detail. It doesn't matter. This is not anything to do with the contract's proposal. This is just my attempt to make this all work and hang together. The bit to notice is that the violation handler is itself a function pointer, which means we can replace it with something else. We've got a default violation handler, just prints it out and aborts. But we could, for example, very useful for testing, replace that violation handler with one that throws instead. You see at the top, we're throwing that logic error, which means we can actually test our contracts. Normally they would abort, but just for testing, we can say, no, make this one throw. That's really useful. And people that have had their own contract libraries have been doing this for years. And there you can see now that's an exception instead. There is a little bit of a problem that we need to be aware of. If we go back to looking at this signature, and if we make the return value a string view instead, because we know that everything is in global memory, that should be stable. Apart from that contract check, there's nothing in here that should throw. And we might be tempted to put a no except on there. But now you can see, hopefully, because of what we just said, because we can replace the violation handler with something that throws, that's going to come into conflict. So if we do try to test that, it's not going to work. It's going to abort because of no except catching the exception. So take the no except off and this all works. This is the essence, or at least part of what's become known as the Lacoste rule. It's actually been around since early C++ 11 days, been applied to the standard library. But more recently, it's become more sort of proposed as a general principle for library design or in general. To quote from this paper, so I think this really captures it. Absent a vanishingly rare and compelling engineering reason to do otherwise, deviating from the Lacrosse rule is invariably and absolutely a terribly bad idea, especially within the C++ standard library specification. So it was holding back a bit there, I think, but gives you an idea. What's really the problem here? No except was really originally put in to allow us to provide move semantics. Because move operations, the move constructors, move assignment operators, usually should be no throwing. They usually can be. And if they are, we can detect that and have more efficient, particularly stood vector, maybe other containers as well. That's why we should always put no except on our move constructors if we can. That's great. That's what it's for. Pretty much anything else, it's going to come into problems like this. There's other problems as well. So don't use no except for that sort of thing. But here's my list of workarounds. So the first one is to follow the Lacrosse rule. Don't use no except. Well, I've said with preconditions you want to test, but actually in general might be a better way to phrase it. But if you do need to, if you've got simple preconditions like the ones we've been looking at, like that is valid month, maybe just test that rather than the functions that use it. And then you can put no except on the functions, but not the predicates. Or consider that overload, the checking policy idiom thing, the thing with the enum and the template. Because that lets you check the throwing version in test code and be reasonably sure that's testing the actual checks. Some other things that people do, which I don't advise so much. Wrap no except in a macro. Compile it out to something different for testing purposes. Not a good idea. Or use def tests. Google Test has these. Can be useful if you want to test that something aborts, but really slow, so you don't really want to be testing contracts that way. So by default, follow the Lacrosse rule. I'm out of time, so I'm just going to rush through my summary. Those are all the things we looked at. Disappointments where you have predictable errors. You want to handle this. Lots of different ways. Exceptions, it should be your default choice. Optional and expected probably cover pretty much all other cases these days. So learn the monadic operations so you can make better use of those. Talked a little bit about contracts. A narrow contract is one where you have that difference between range and the domain, or other things where there's undefined behavior if you invoke it incorrectly. Preconditions specifically, we talked about these throwing violation handlers, useful for testing. Don't use no except. That has been modern C++ error handling. Thank you very much. Do we have time for some questions?
Absolutely brilliant talk, Phil. Phil Nash, everyone, once again.
Thank you.